Hello and welcome to this next lecture in the pattern recognition course. We have been looking at some basics of statistical learning theory. We have looked at some aspects last time. So, as I said, for the next couple of lectures we will be looking at this. So, just briefly recall what we have done last class. We are actually looking at some formalisms for addressing the issue of generalization. How can you theoretically talk about correctness of the generalizations made by learning algorithm, right? You see, in any learning algorithm, essentially given some examples and it learns from the examples a general rule for classification or regression or a general function of a regression. And the generalization issue is that the algorithm should properly generalize, so that it performs well on new examples which are drawn from the same distribution as the training samples. So, given some training samples, if I am learning a classifier, then similar examples, new examples given to me, I should be able to correctly classify. That is the issue of whether I am generalizing properly or not. Last class we looked at the notion of what is called probably approximately correct learning, what is called PAC learning, and we have presented the entire formalism. We also looked at an example of how we show that a specific algorithm PAC learns a concept class. So, we take a very simple example of a R2 classification problem, what I called learning the concept of medium build persons. Essentially, the target concept is an axis parallel rectangle. We have seen example of trying to learn with two by searching over two different class of classifiers. One is over the set of all possible axis parallel rectangles in R2, and we showed that this algorithm PAC learn. The algorithm simply looks for any classifier in its bag that is consistent with all the examples, and if there is more than one, you take the smallest. This algorithm, if it is searching over all possible axis parallel rectangles, we showed that it PAC learns, whereas if we change it to searching over every possible classifier, two class classifier over R2, then it does not PAC learn. Okay. So, let us start by briefly recalling the PAC learning framework, so that we can now extend it. The PAC learning framework is as follows. We are actually given the instance space which we denoted as script X. So, all your feature vectors are input to your learning algorithm is an element of the instance space or script X. It is also called the input space. Y is the output space, that is the set of class labels. If you are considering two class classifier, Y will be either the set 0 comma 1 or the set plus 1 comma minus 1 and so on. And a script C is said to be concept space. It is a set of subsets of X. It is a subset of C itself, is a subset of the power set of X. So, elements of C are subsets of X. So, we have taken some specific subsets of X and called it the concept space or the set of classifiers. This determines what class of classifiers we are searching over. Okay. And we are given examples where Xi are drawn IID according to some unknown distribution P x and x, and Yi is obtained by classifying Xi using a one particular element from C, which is called C star. C star is the target concept. Of course, we do not know C star, we do not know P x, but we know X, Y and C. So, we are searching over C to find a good approximation to C star based on the examples Xi, Yi given to us, that is the set of examples S. So, given the set of examples S, we have to search over the concept space C to find some classifier, which we hope will be a good approximation to C star if there are enough examples given. Our notation was that if I am learning with S, S has exactly n examples. So, after seeing n examples, I output some element of C, which is denoted by Cn. Now, the issue of correctness is addressed as follows. We say the algorithm PAC learns the concept class C if given any epsilon delta, there exists some n. So, that probability error C n greater than epsilon is less than delta for all n greater than n, which essentially means error C n converges to 0 in probability. That is what this means. Okay. So, essentially given sufficiently many examples with a large probability, I make less than epsilon error. Error less than epsilon is greater than 1 minus delta. So, with a large probability I can make I will make small error. this must be true for every epsilon delta. You give me the accuracy to which I have to learn, that is epsilon, and the confidence with which I have to learn delta, then I will give you a set of number of examples I need. If you give me that many examples, I will always be able to learn to that level of accuracy and confidence. Okay. No matter what the distribution P x is and what the target concept C star is, as long as C star is in C. Right. Where error is defined as the P x probability of C n delta C star. What is C n delta C star? The symmetric difference between the set C n and C star. So, the set of all points that are in C n, but not in C star not in C n. So, these are essentially C n delta C star consists of the set of points in X, where the classification by C n and C star will differ. So, we are asking what is the probability assigned to that set of points under the distribution P x, right. That is the probability of C n making an error on a randomly drawn sample, when the random sample is drawn according to distribution P x. Because our samples are IID with respect to P x, we are also testing our generalization on samples drawn with respect to P x. That is why this is the proper definition for error. Of course, as we see in error, C n itself is a random variable, because it depends on C n, which in turn depends on the random n samples that we got in the sample set S. Okay. So, pack learning probably approximately correct is I learn an approximately correct classifier with a large probability. Of course, I written it the other way, we learn a approximately incorrect classifier with a small probability, that is with a large probability we learn a approximately correct classifier. As we see in last class, whether an algorithm can pack learn or not depends on the complexity of the class of classifiers we are considering. So, we see in an example where everything else is same, but if we search over C 1, then the algorithm pack learns. If we search over C 2, the algorithm does not pack learn. So, essentially if the class of classifiers is too complex, then I may not be able to learn anything. Okay. That is what we gathered from the illustrative example problem that we considered last class to explain pack learning. Now, the concept of pack learnability is a very interesting concept, which historically it is at least in computer science circles, this is the first ever time people formally address the issue of correctness for learning. As I said, statistical circles, it was there even in 60s or at least early 70s, similar concepts are there. That is what we are going to look at next. Pack learnability, the reason why we start with pack learnability is easy to understand. It is very simple framework. It allows one to properly define what is correctness of learning, allows one to ask questions like whether a given algorithm learns correctly. We have seen an example of showing that an algorithm learns correctly and showing that an algorithm does not learn correctly. We can, in the proof that we are given about showing the example learns correctly, we also seen how given an epsilon and delta, we can actually calculate or bound the number of examples that we need to learn to that given level of accuracy and confidence. So, this number of examples needed as a function of epsilon and delta is often called the sample complexity of the learning algorithm of the learning problem. So, the pack learnability also allows us to calculate complexities of learning problems, which in turn means that we can calculate complexity of different learning problems, and hence the pack framework allows us to appreciate which learning problem given different learning problems, which are more complicated, that one problem is more complex than the other and so on. So, we can get an appreciation of the relative complexities of different learning problems. Right. Having said this, the inadequacy of pack learning is that it deals with what can be called an ideal learning situation. What is ideal about pack learning? We assume that there is a God given classifier C star, right, and that C star is in our C, in our class of classifier that we are searching over, right, and the examples are all noise free and perfectly classified, which means at any given time over the class of classifiers I am searching, there is at least one classifier that correctly classifies all examples, right. This is both these are really difficult assumption to satisfy, that the God given correct, even if there is a God given correct classifier, that it is there in the bag of classifiers I am searching over, because beforehand I do not know what classifier structure would perfectly solve this problem, and that all examples are perfectly classified is also not a very nice assumption. So, next we consider an extension of the PAC framework, so that we can analyze more realistic learning scenarios, where we do not have to assume that there exists a target concept with respect to which all examples are actually classified, and we can take care of at least the ordinary noise that we expect in any examples for any classification problem. Okay. So, let us now describe this new framework. Essentially, we are going to extend it in such a way that we do not have to worry about C star, and we can talk about examples are not perfectly classifiable. That means, same x may come from different classes with different probabilities. So, the notation for the new framework is as follows. As earlier, we have the input space x, which is the feature space, the output space y, which is set of class labels, or it will be equal to R if I are considering regression problem. Now, we have what is called a hypothesis space. This is going to be our family of classifiers. Of course, it is not just that we changed the name from C to H. We are not assuming that H is necessarily a subset of 2 power x. Instead, what we will do is each element of the hypothesis space is some function that maps x to some other set A. If we take y to be 0 1 and every element of H maps x to 0 1, then it is same as H being a subset of 2 power x and is same as constant. But here we will make H such that each element of H is a function that maps x to some other set. We will call that set A, which stands for action space. We will currently see why this will allow for many different learning situations to be incorporated. Another difference is now the training set xi yi of n examples is drawn IID according to some distribution p x y and x cross y. We are not saying you first draw from x and then classify with a God given classifier C star. Now, training data is obtained by sampling from x cross y using some distribution p x y. Once again, like p x in the other case, we do not know p x y, but the training set is drawn according to some distribution x cross y. Okay. So, let us ask what does this framework give us extra. The first thing, as I said, we have done here is we have replaced what we call concept space C with the hypothesis space H. C was defined to be 2 power x, we are taking y to be 0 1 and we are searching over 2 class classifiers only. But now, so what it means is in the new setup, each element of the hypothesis space H is a function that maps the input space to the action space, right. Now, first let us see that if I take A to be equal to y, which of course I can, then it is same as L A, then H becomes same as what we call C earlier. Okay. But because we can choose A, it allows for taking care of many situations. For example, suppose y is still 0 1, a 2 class classifier, but let us take A to be R. Then what I am actually learning are functions on H that take real values, for example, a discriminant function. So, I may be learning a discriminant function that maps x to real numbers, does not map x to 0 1, right. I can use the discriminant function to classify ultimately, but I am searching over the class of discriminant functions. Now, that I can easily incorporate by taking my action space to be R, even though y is equal to 0 1. Only the examples have to come from x cross y. So, I can't take y to be R, because the examples come from class 0 or class 1. So, examples still come from x cross y, but the learning algorithm is searching over functions that map x to real line. Okay. So, for example, I can easily incorporate learning of discriminant functions here, which I could not have done in the earlier one. So, in particular, once again as an example, not that it is always easy to do this, as an example you can think that when I take A to be R, right, I am actually learning real valued functions. So, which means I can ultimately think that sin of h x will denote the class label, because I am still considering two class problems, and the magnitude of h x may give me some measure of confidence in the assigned class. So, suppose x should be in class 1 and h x is positive. If h x is 10, then I would say I have a lot more confidence that x is class 1 rather than when h x is at n power minus 3, it is just greater than 0. So, in some sense I may be able to use learning problems which actually deal with such things. We will see later on in this course that we will actually do this. We use measure of value of h x sometimes as a measure of confidence. Okay. So, this is one extra thing that this framework gives us, the flexibility in choosing y. We will see a few more examples, choosing A, the action space. We will see a few more examples later on. The second change in our framework is that the examples are drawn from x cross y, by x cross y I mean the Cartesian product of the sets x and y according to some distribution p x y and x cross y. This allows for much of natural noise in the training. See, for example, in the in the two class classification problem, the two class conditional densities may overlap. What does that mean? When we actually generate the training data, we generate it by sampling from one class conditional density or the other class conditional density, right. So, which means that the same x can come from different classes with different probabilities. This, for example, is not possible if I have to assume that there is a C star, because C star is a function. Given an x, x has one God given class label, but that is in general not true. When class conditional densities overlap, my samples never satisfy this condition. But now this is very nice, because my examples are only drawn from x cross y according to p x y, and there is no God given classifier. This natural thing that happens in all classification problems is taken care of. Okay. Of course, in general, given the joint density of any two random variables x and y, the p x y can always be factorized as to the marginal density of x, marginal distribution of x, multiplied by the conditional density y given x. Now, if p y given x is a degenerate distribution, what does that mean? For a given value of x, because the conditional density, only one value of y has non-zero probability and all others have 0 probability, that is when p y given x is a degenerate distribution. That is same as having a God given classifier. For a given x, there is only one possible y. But in general, when class conditional densities overlap, the p y given x is a proper density. For the same x, different y come with different probabilities, right. So, because we can always factorize like this and we can assume p y given x is a degenerate distribution, the whole PAC framework is still part of this new framework, right. This new framework is a proper extension of the PAC framework. The PAC framework can be still considered a special case of this, but we get more flexibility in modeling learning situations. Okay. So, having examples drawn from x class y using a distribution allows for many more scenarios such as overlapping class conditional densities and many more. Now, moving on, like earlier, what does the learning machine do? It takes a training data consisting of an examples as input and output some hypothesis from H now. Earlier as a concept, now it is searching over H. So, it outputs some element of H, let us call it H of n. So, H subscript n is what the learning algorithm or learning machine will output given training data consisting of n examples. Now, to rate H n, how do we rate H n? Earlier there is a God given target concept. So, we can say is H n close to the target concept in terms of classifying new examples, but now there is no target concept. So, we have to find some other way of defining whether the goodness of H n. We have already done it in the beginning of the course. We introduced briefly the idea of loss functions. We used a loss function, the 0 1 loss function, while developing the base classifier, but that time we have not done this very formally. So, that is what we are going to do now again, but a little more formally now. Since now to appreciate why you need loss function is not only that there is no notion of a target concept, In general, there may be no H that is consistent with all examples. So, we cannot even say that the classification accuracy of H on the samples is a good indicator of how good it is, because maybe the best possible classification accuracy does not give you 100% accuracy, right. So, there may be no H that is consistent with all examples. So, we need a different way to rate different H, and for that we use the idea of loss functions to rate different H, and hence we define the goal of learning. So, what is a loss function? We already, as I said, we already encountered loss functions earlier in the course. A loss function in our new notation now is a function whose domain is y cross A, the Cartesian product of the output space y and the action space A, and maps it to R plus, the positive real line. Okay. So, the idea is L of y comma h x, L as a function of two variables, one is in the space y, the capital script y, that is the for example, the classification problem classification labels, and the other is in the range space of the functions h over which you are searching. So, essentially on a random sample x y, a particular hypothesis h, it would say h of x, whereas it should have said y. So, L y comma h x is the loss suffered by h on a random sample x y. Okay. This is how we earlier also introduced loss functions. In general, of course, we can make the loss function also depend explicitly on x. So, we can write loss function as L of x comma y comma h x. What it means is, for example, in different regions of the feature space, we may choose to measure loss in using different criteria, okay. Depending on the application, that may be important. So, we could actually take loss function to have a domain which is x cross y cross A. Most of what we say here in this course will also hold for these more general loss functions, but to keep notation and other things simple, we will only going to look at loss functions as a function of only y and h x. Also, by convention, we assume that the loss function is non-negative, as the range space of loss function R plus, because we are considering it as loss, we assume it to be always non-negative. Matter of fact, later on we assume loss function is bounded. So, that bounded on one side anyway is bounded by 0, we assume is bounded on the other side also. Okay. So, given this, what is it that we want? On random samples x y, h suffers a loss L of y comma h x. Now, I have learned from samples drawn according to distribution p x y using the same idea of fairness that we use in pack learning. Now, I can say that a h is good if on samples drawn according to p x y, its average loss is small, right. That is how we are going to define the goal of learning. Essentially, on samples drawn according to the same distribution p x y, our hypothesis that have low average loss are better. So, we define a function R that maps h to R plus, that means it assigns a real number to every hypothesis. So, it is essentially a functional. By R of h is expected value of L y comma h x, where expectation with respect to p x y. So, that is the expectation integral. This is like a Riemann-Stieltjes integral, but anyway, this is essentially a expectation integral with respect to the distribution p x y. So, R is called the risk function, right. So, R of h is called the risk of h and R is called the risk function. What is risk? Risk is expectation of loss, where the expectation is with respect to p x y. So, the samples are drawn with respect to p x y, and I measure goodness of h with the average loss h will suffer on samples drawn according to p x y, because risk is expectation of loss, where expectation with respect to the same distribution p x y. So, if we have a h with rho or h, that is a better classifier, right, because on the average on similar samples it suffers low loss. So, this is what we are going to use to define the goal of learning. So, the goal of learning is to find a h that minimizes risk. So, the goal is find the minimizer of the risk function. Okay. So, let us formalize this. Let us denote by h star the the overall script h, find the minimizing h to R h. So, that is arg min h belonging to h R h. So, h star is nothing but the global minimizer of risk. R h star is the global minimum of risk. So, h star is the global minimizer of risk, and we define the goal of learning as finding h star, the global minimizer of risk. In a given learning problem where you are given x, y and a and the loss function, and p x y is arbitrary, h star may not be unique. There may be many different h star, all of which achieve the global minimum, but it really does not matter. For us, risk is what we want to minimize. So, any h star that minimizes the risk is same, and we are going to compare different classifiers only in terms of the risk value that they have, and hence whether or not h star is unique does not concern us, right. H star may be unique, may not be unique, but the goal of learning is to find a global minimizer of risk. So, risk minimization is a very general strategy adopted by almost all machine learning algorithms. Everything that we considered so far, all our linear classifier learning algorithms are essentially risk minimization algorithms, right, under a particular loss function. Many other algorithms that we consider later on in the course can all be viewed in this general framework of risk minimization. Okay. But minimizing risk is not a easy problem, because we have no knowledge of p x y, and R of h is expectation of L y comma h x with respect to the distribution p x y, and since we do not have p x y, given a h I cannot calculate R of h. So, how can I minimize R? Minimization of R directly is not feasible, because I cannot even calculate R h given a h, because our definition of R h involves an expectation integral with respect to p x y, and I have no knowledge of p x y. So, what do I do? As we already seen briefly in the beginning of the course, we define another function which I am calling empirical risk function, where we call it R hat of n. If you recall our notation from the estimation part of this course, when we consider various methods of parameter estimation, a hat denotes an estimate of some quantity. So, I do not know R, so I am estimating R. So, this is R hat, and the subscript of an estimator denotes the sample size, because I am estimating it with n examples, n is the subscript. That is why we call this function R hat of n, which also assigns a real number to every h, and that number is simply 1 by n summation I is equal to 1 to n L of y I h of x I, where x I y I is equal to 1 to n is the sample set, right. So, R hat n is nothing but the sample mean estimate of the risk. Actual risk is the expectation of L y comma h x. If I can't calculate this expectation, but I have IID samples y I h x I, then I can approximate this expectation by its sample mean, right. That is what we are doing. This is the sample mean estimator of risk obtained from n IID samples. That is why it is called R hat. So, the idea is that sample mean is a good estimator. So, R hat n h would be close to R h. So, because I can't minimize R, I minimize R hat n. So, let the global minimizer of R hat n be h hat star n. Well, this is quite a mouthful. The reason why we chose what might look like a strange notation is the following. What is our goal? H star. We do not know H star. We want to estimate H star. So, the estimator for H star will be H hat star, right. A hat always denotes estimate. So, this is estimating H star, and n is the sample size. So, H hat star n is the estimator for H star based on n samples, and that is nothing but the global minimizer of the empirical risk R hat n. Okay. Now, given a particular h, because the samples are there and I know the loss function, I can always calculate this, right. Let us remember that the loss function is known to us, hence given a h we can calculate R hat n of h, which means in principle we can always find H hat star n by optimizing R hat n. Of course, it depends on what the loss function is, that is the summation in the empirical risk minimization may be simple to minimize, may be complicated to minimize. We do not know the parameterization for H, how complicated different H functions are, but all that apart, in given any H I can calculate R hat and H, the expression is there. Hence, in principle we might be able to find H hat star n by optimizing. Okay. So, this is a very generic strategy followed by all algorithms. We essentially want to do risk minimization, but we can't do risk minimization. So, we do empirical risk minimization, that is we are approximating H star by H hat star n. This is the strategy used by all machine learning algorithms, or at least most of the machine learning algorithms. Okay. So, the question is, if I did this, is H hat star n a good approximate of H star? Right. This is called the question of consistency of the empirical risk minimization. I actually want to minimize risk, I can't. So, I am minimizing the empirical risk. So, I am asking, is this consistent? If I find the minimizer of empirical risk, is that a good approximation to the minimizer of the true risk? Is H hat star n good approximate of H for large enough n? Right. This is the question we want to ask. We already know this question is not trivial, even in the simple situation when we have pack and a target concept. We have exhibited concept classes where this H hat star n is not a good approximate of H star. Okay. So, the issue is we are going to develop some ways of addressing the issue, or at least understanding when H hat star n would be a good approximate of H star. So, before we go there, we can now sum up the whole idea of empirical risk minimization as saying that any learning problem has two parts. The first part is an optimization part, that is find H hat star n. So, once I start with a loss function, I choose a loss function, I specify a loss function, then I can calculate given the samples, I can calculate the empirical risk. So, now that is a optimization problem, one needs clever algorithms, the optimization problem may be very complex, we have to find efficient ways of dealing with it. So, that is one half of the learning problem. Find the minimizer of the empirical risk. The second half of the learning problem is the statistical part. Now, to minimize R hat n, I have to decide what is the range of H, what is the domain of R hat n, that is over what class of functions H am I optimizing R hat n. Now, while I can choose it to make the optimization problem simpler, I should also pay attention to, so that I choose it so that it becomes a good approximate of H star, that is the statistical part. Okay. Right now, we are asking the statistical question. How can you say, for what kind of H's can you say H hat star n will be a good approximator to H star? Before we go there, let us look at a few example loss functions. We only looked at 0 1 loss earlier, we will look at a few more example loss functions. The loss function is chosen by us, right, it is part of the specification of the learning problem. So, we can choose loss functions for whatever reasons. The loss function is essentially intended to capture how we would like to evaluate performance of our classifiers, right. So, a loss function tells me how we rate H x versus y, when y is what I should have said, but I said H x, right. So, it is our specification of how to evaluate performance. Okay. So, we run through a few loss functions. Let us go back to the 0 1 loss function. Let me consider only the 2 class classification problem, though it can be done for multi-class also, as we know. So, take y is equal to 0 1, and in this case we take a is equal to y. So, the class of classifiers over which you are searching are actually classifiers, they are binary valued functions on x, that is what taking a is equal to y means. Now, the 0 1 loss function is defined by given any y and h x, L of y comma h x is the indicator function of y not equal to h x, that is if y is not equal to h x, it is 1, if y is equal to h x, it is equal to 0, that is what I of a is indicator of a means. If the event occurs, then its value is 1, otherwise value is 0. So, L y comma h x is 1, if y is not equal to h x is equal to 0 otherwise. Okay. So, that is the 0 1 loss function. Because risk is expectation of loss, if I want to find risk of h, this is the expectation of this is a binary random variable. So, the expectation is nothing but the probability that it takes value 1. So, R of h is probability y is not equal to hx, that is when this random variable the indicator will take 1. So, R h is nothing but probability y is not equal to hx. So, risk is nothing but the probability term misclassification. So, h star minimizes probability term misclassification. So, if I choose 0 1 loss function and set over a class of classifiers, that only because we taken a is equal to y. Our goal of learning is a function h star or a classifier h star that minimizes problem misclassification. So, that is a very nice, very desirable goal. For example, that is what we did for base classifier, right. H star minimizes probability misclassification if I choose 0 1 loss function. Now, in defining this, so far we assumed that we are searching over class of binary valued functions. We have taken a to be y, right. We do not have to, that is the beauty of our formalism. We can extend this, for example, to take discriminant function learning. What do? We take a is equal to r. Instead of taking a is equal to 0 1, we take a is equal to r. Now, each h is a function that maps x to real line. So, it is a discriminant function. So, we are searching over the family of discriminant functions. So, now we can define the 0 1 loss as L of y comma h x is indicator of y not equal to sin of h x. So, even though we are learning over h x, the loss depends on only on y and sin of h x. So, we will define L on y cross a, that is 0 1 cross real line, but given a y and h x, the loss value is 1 if y is not equal to sin of h x is 0 otherwise, right. This will allow me to extend the 0 1 loss to loss function even to the case of learning discriminant functions. Okay. There are a few other interesting things that we can do here. First, either in this or in the earlier case where we assume h x itself is binary, so I can write y is equal to h x. Essentially, if I classify correctly, the loss is 0, if I classify incorrectly, the loss is 1. 1 is of course arbitrary, right. Instead of 1 I can take 10, it makes no difference. So, having any fixed misclassification cost is essentially same as 0 1 loss, right. We have already seen that. The 2 is, even when we take a is equal to r, even when we consider discriminant function learning, the 0 1 loss compares only sin of h x with y. The magnitude of h x has no effect on the loss, right. This is a very important property of the 0 1 loss function. It only depends on correctness or otherwise of the classification you can do by using the function h, right, because it only compares sin of h x with y, which for example means sometimes I classify h x correctly with a high confidence, does not give me any extra brownie points, right. I classify correctly or not is all that 0 1 loss function can. While at this point it may not be clear whether it is good or bad, it turns out that this makes 0 1 loss function more robust to noise in classification labels. So, even if sometimes some of the labels given are wrong by mistakenly given in my training set, minimizing empirical risk or risk under 0 1 loss function gives me some robustness in noise. We currently won't consider it, maybe later on in the course if occasion arises I will show you why. So, 0 1 loss is intuitively appealing. It under 0 1 loss the best function h star is one that minimizes probability of misclassification. So, it is intuitively appealing, but minimizing empirical risk under 0 1 loss function is a hard problem. Firstly, 0 1 loss function is non-differentiable and hence empirical risk function is also non-differentiable. So, optimizing a non-differential function is that much more complicated. And the empirical risk minimization, the 0 1 loss often turns out to be a non-convex problem. We will see it shortly, a little while, give you some basic idea of this non-convex series loss functions later on. Okay. So, because a non-convex optimization problem, the optimization is always a little more complicated. And there are many other loss functions which are used to make the optimization problem easier. Okay. So, look at just a couple of them, there are others which we will see through the course later on. One is one that you already know, though we may not have explicitly emphasized the loss function aspect of it. It is called the squared error loss function, defined by L y comma h x is y minus h x whole square. Right. As is easy to see, the linear least squares method is essentially empirical disk minimization with squared error loss function. What are we minimizing? I is equal to 1 to n y I minus h x I whole square. So, that is nothing but the empirical disk except for the 1 by n factor. As we said, when we consider linear least squares method, that 1 by n factor makes no difference. So, the linear least squares method we considered, linear least squares classification, regression, all of those are essentially empirical disk minimization with squared error loss function. Of course, for a 2 class classification problem, as you have seen, we can take y at 0 1 or plus 1 minus 1. We take a is equal to r, right, where we have considered h of x, which is a affine function w transpose x plus w naught. So, we have taken a to be r. So, each h a discriminant function. As you have seen, this kind of empirical disk minimization is feasible only under a new framework, not under the PAC framework, right, because we take a to be r here. All the functions for which you are searching are all real valued functions. Okay. Of course, we can also use square error loss for regression, in which case we take y to be real line. Another interesting scenario in under square error loss is you take y to be 0 1 and a to be the interval 0 comma 1. Then what happens? Each h is a function taking values in 0 1. So, we can interpret it as a posterior probability function, right. Given x, what is the posterior probability of class 1 for x? Now, we know that under square error loss, the minimizer of the expectation of the square of error is the conditional expectation, and hence is the posterior probability function. We have already seen it when we considered the linear least squares. The minimizer of the expectation of the squared error is the posterior probability function, right. Now, we are searching over, if I take a to be 0 1, then we are searching over all possible posterior probability functions, and hence risk minimization now will look for a function in h that is a good approximator for the posterior probability function, right, something like the logistic regression. Empirical minimization of squared error is a convex optimization, turns out to be convex optimization problem for linear models that we have already seen. The linear least squares is a convex optimization problem. The squared error loss is also very often used in many learning algorithms. For example, much of neural network based classified learning is empirical disk minimization under squared error loss. Here is another loss function, I called it soft margin loss or hinge loss. We will come across this when we do what are known as support vector machines. We briefly consider that in the introductory classes. So, for here we take y to be plus 1 minus 1 and a is r. So, each of my h is a real valued function, and loss of y comma h x is given as max of 0 comma 1 minus y times h x. Essentially, because I take sign of h x to be the classification, and I am taking y to be plus 1 minus 1. If y into h x is positive, right, then my classification is correct, and y into h x is negative, my classification is wrong. So, if y into h x is greater than 0, then classification is correct, but even if y into h x is greater than 0, I may still suffer some loss. Till y into h x reaches 1, the loss is not 0. Y h x greater than 1, the loss is 0. Y h x less than 1, the loss is not 0. Of course, y h x less than 0 also loss is not 0, but if y h x is greater than 0, the classification is correct. This also is an interesting loss function and results in a convex optimization problem for empirical disk minimization. Okay. We considered 3 different loss functions, 2 of them we already seen earlier and one which we have not seen earlier, and we can look at the other 2 loss functions like many others that we come across later on as convex approximations of the 0 1 loss function, right. To look at this, what we will do is we take y to be plus 1 minus 1 for a 2 class problem and write all loss functions as functions of a single variable which is denoted by y into h x, because even we in general take a is equal to r. So, h x is a real valued function, but because you are using sign of h x as the classifier, if y into h x is positive, then y and h x are the same sign, is negative, y and h x are different sign. So, y into h x as a variable denotes both correctness of classification and any magnitude that we are talking about. So, we can rewrite all loss functions as single variable y into h x. If we write that for the 0 1 loss, L y into h x is 1 if y times h x is negative and 0 otherwise. If it is negative, then classification is incorrect. So, loss is 1. If it is positive, the classification is correct. So, loss is 0. The square error loss can also be written as 1 minus y into h x whole square. If y is plus 1, then this is anywhere true. If y is minus 1, then originally y minus h x whole square is minus 1 minus h x whole square, which is same as 1 plus h x whole square, which is same as 1 minus y h x whole square. So, square error loss can also be written like this, and the soft margin or hinge loss is anyway written as a function of y times h x. Now, because all three functions are function of one variable, we can plot them, right. So, that is the step function is the 0 1 loss. This line, right, it see my hinge loss is 1 minus x. So, for x less than 1, it goes like this, x that y into h x greater than 1, it is 0. So, did not mark the axis here, but on the x axis I am plotting y into h x, on y axis I am plotting L y comma h x, right. So, that is the hinge loss, and this parabola is the familiar square error loss. One way of looking at it is, if I look at this 0 1 loss function, this is non-convex, because if I take a point there and a point here and join them. So, for a convex function, if I join any 2 points on the curve, the entire curve between them is below the straight line. But here, if I take a point here and I take a point and join them, right, part of the curve is above the line, part of the curve is below the line. So, this 0 1 loss function is non-convex. So, you can think of the hinge loss or the square error loss as kind of approximating this 0 1 loss function, so to say, but convexifying it, right. So, for example, the hinge loss tries to come up till here and then push it like that, so that it becomes convex. So, all the other loss functions, all the other two loss functions here can be thought of as trying to find a convex approximation to the 0 1 loss function, okay. And essentially that is why minimizing empirical risk under these loss functions is much easier than under the 0 1 loss function, okay. These are used for classification mostly, what we have seen, though the square error loss is also used for regression. There are also other loss functions which are used more in regression. For regression also you can use square error loss, but is very sensitive to data errors. In square error loss, the loss is y minus x. So, suppose I am fitting a straight line. If I have got 4 points, 3 of them are close to a straight line, but fourth one is very far away. Now, if I take the intuitively obvious straight line, because the fourth one is far away and I take square of the distance, the risk for it, which is the sum of all the squared errors, will be very large. On the other hand, if I move the line towards the outlier, then maybe all the errors will become intermediate. So, the square of the errors might be much smaller. So, the square error loss becomes very sensitive to data errors such as outliers. There are other loss functions which are better from the from such robustness point of view. Just for completeness, here are two. A simple way to make squared error more robust to outliers is, instead of taking square, you take absolute value. Absolute value does not go as fast as square. That is the reason why it is a little less sensitive to outliers. But obviously, optimizing absolute value is a harder problem than optimizing square, okay, because this is non-differentiable. There is another loss function that we will once again consider when we look at SVM kind of methods for regression, is called the epsilon insensitive loss. Essentially is once again like the hinge loss. I predict h x as the target, y is the true target, y minus h x absolute value is the error. If the error is less than epsilon, then I suffer 0 loss, otherwise I suffer a linearly growing loss, right. So, this is called an epsilon insensitive loss, which also has some interesting robustness properties and also makes the optimization problem, resulting empirical risk minimization problem, a convex optimization problem, okay. So, as you saw, there are many different loss functions one can think of. Many of them also make the empirical risk minimization problem efficiently solvable. That is the reason why we choose them. that the choice or loss function can efficiently tackle the optimization part of learning, right. But let us get back, we will see many algorithms for this later on anyway. So, let us get back to what we started with, the statistical part of the learning problem, right, the consistency of empirical risk minimization. So, our objective is to find H star. Let's once again briefly review the issue of consistency. Our objective is to find H star, the global minimizer of risk. We do not know how to minimize R, we do not even know how to calculate RH for any given H. So, we minimize the empirical risk R hat n instead of R, right, because we know how to calculate R hat n, we know how to minimize it. So, because I can't minimize R, I will minimize R hat n, and hence I find H hat star n. So, we for our approach to work, we want H hat star n to be close to H star, and we already know what close means by our experience back learning. Close only means in terms of their classification accuracies on new samples, and that is given by risk. So, what we are interested in is the risk of H hat star n same as risk of H star. Risk of H star, of course, H star is a unknown but fixed function. So, R of H star is some constant, but what I am learning is H hat star n. So, I am asking is the true risk, which I cannot calculate, but is the true risk of H hat star n, does it converge to H star? The convergence is as n tends to infinity. Of course, like in the case of pack learning, we know H hat star n is random, because it depends on the random sample, right. So, because of that, R H hat star n is a sequence of random variables. So, we have to define in what sense this convergence is, and like in the pack case, we take convergence to be in probability, but essentially the question is that the risk of the true risk of the minimizer of the empirical risk, does it converge to the global minimum of true risk. Okay. That is what consistency of empirical risk minimization about. What is the reason why we think empirical risk minimization works? Sample mean is a good estimator, and empirical risk is simply sample mean estimator of true risk. So, for any given H, R hat n H converges to R H if n is large. So, for every H, whether I calculate R hat n H or R H, it should not make much of a difference, right. This is the law of large numbers, because we only want convergence probability is weak law of large numbers. Weak law of large numbers says that the sample mean converges to the expectation of the random variable. So, for any H, R hat n H as n grows will become very close to R of H, because the true risk of any hypothesis can be approximated by its empirical risk like this. It stands to reason that if I minimize this, it should be okay as minimizing this. But this convergence does not mean that R of H hat star n converges to R H star. It only says R hat n of H converges to R of H, they are the same H. Here I am not worried about R hat n, but I am asking R of some other sequence around H hat star n, does that converge to R of H star? So, a priori there is no reason why the law of large numbers should imply this, right. Our reason, intuitive reason for preferring empirical risk minimization is law of large numbers in our mind. We know that for sufficiently large sample, R hat n of H will be close to R of H, and hence okay, it is all right, minimize empirical risk. But we also know that this convergence says nothing about whether R of H hat star n converges to R of H star. So, what we are interested in is that the risk of the minimizer of empirical risk, that the true risk of the minimizer of empirical risk, does it converges to the global minimum of true risk. Okay. Let us consider the familiar scenario, the examples we see in last class to appreciate this a little more. Let us take a and y to be 0, 1. Let us suppose we use 0, 1 loss function, and examples, let us assume that the examples are actually generated by drawing them from x using a p x and then classifying using a particular function, let us call it h tilde in h. In general, I want p x y, but this only means that I am taking p x y to be p x into p y given x and p y given x is G-general distribution. As you already seen, doing this is within our framework. So, suppose the examples are drawn according to some p x on x and classified using a h tilde. Now, I am using 0, 1 loss function. 0, 1 loss function's risk is probability times classification, and every example is of course classified according to H tilde, right. So, the global minimum of true risk is 0 and one of the elements of H that achieves this global minimum is H tilde. Of course, there might be others as we said, but we certainly know R of H tilde is 0. So, and global minimum of risk is 0. So, we will be happy learning any H such that R of H any H hat star n so that R of H hat star n ultimately goes to 0 as n tends to infinity. That is what we want to do in this scenario. Let us ask, is that feasible? Because of this case, my risk is the expectation with respect to p x y, but p x y is essentially only p x is random. So, my risk under 0 1 loss function. So, it only ask me risk of any H is the p x probability of H delta H tilde. As we already seen, if we take p x y to be actually p x and p y given x is degenerate, then our new framework is same as PAC framework. So, the risk under 0 1 loss function of any H is same as p x of H delta H tilde. That is, this scenario is roughly same as what, not roughly, actually same as what we consider in the PAC framework. Now, under 0 1 loss, the global mean of empirical risk is also 0, because H tilde is in H, I am searching over H, there might be others, but certainly H tilde gives me 0 value for empirical risk under any samples. So, the global minimum of empirical risk is also 0. Of course, for any given n, there may be many H other than H tilde with R hat n of H is 0. Now, what is my optimization algorithm to do? There are many H's, so I have to choose any one. So, my optimization algorithm chooses some general rule to output such a hypothesis, right. Like for example, the smallest H as we considered in our example last time. So, now we are close, we are same as our previous example. So, if I take H to be 2 power x, then the same as the example we considered earlier, and hence we know that H hat star n delta H tilde p x probability of this will not go to 0 with n, right. That is what we showed last time in the PAC example. Thus, in this scenario, my minimizer of the empirical risk, the true risk of the minimizer of the empirical risk will not converge to the global minimum of R H, right. Of course, the law of large numbers still holds. Even in this case, even if I take H equal to 2 power x, law of large numbers holds for any specific H, R hat n H still converges to R of H, but that is not good enough for this to happen, right. So, we know that simply because the law of large numbers guarantees that sample mean converges to population mean, it does not mean that the risk of the minimizer of the empirical risk converges to the global minimum of risk. And as we saw in from our PAC example, it depends on the choice of H. If we choose one H, it happens. If we choose another H, it does not happen. Hence, the statistical question is, for what H is empirical risk minimization consistent? Consistent means given any epsilon delta greater than 0 exists a n, so that R of H hat star n minus R of H, this difference being greater than epsilon has probability less than delta. So, this is the question of empirical consistency empirical risk minimization. In the next class, we will see how can we answer this in a sound statistical sense. Thank you.